Swayam Prabha. Digital India. Educated India.
Welcome back to another lecture of this course on robust control. So in the previous lecture, we've begun to see this properties of convex sets, right, and why they are such a desirable class of sets, right. We've seen that, the last result we saw is that if you have in particular two convex sets, right, then it's pretty easy to figure out whether there does exist a hyperplane that separates those two convex sets, okay. So what is the condition that we figured? If two convex sets are disjoint, that is if their intersection is non-empty, then we saw that there always exists some hyperplane that will separate Q1 and Q2. Of course, you might be able to separate two sets, not necessarily using hyperplanes, but then if you can do them using hyperplanes, that makes things much easier, because we have seen how we can define hyperplanes, using the objects called linear functionals, right. So we assign certain values to linear functionals, and the resultant curve or manifold that results is called the hyperplane. We have seen that it is nothing but the kernel of the linear functional shifted from the origin by a certain vector, and that is what gives us or gives rise to these hyperplanes, right. So therefore a hyperplane is uniquely specified by a linear functional and a real number, right. And if we can separate sets using these hyperplanes, it's very simple, and precisely when we have convex sets, that's when it's always guaranteed that if the sets are disjoint, you can always separate them using these hyperplanes, right. So hopefully we've begun to see the motivation behind studying convexity in some detail. Of course, needless to say, as I have said so often in the previous lecture too, that we are not really getting into a very rigorous convex analysis that will entail covering a different course altogether, but we will obviously make use of several different intriguing properties of convex sets, right. In particular, when we indulge ourselves in convex optimizations, right. So there are certain very attractive and desirable features of a convex optimization problem, in that if you're trying to optimize a linear function or functional over a convex set, then it suffices if you find a local minima. The moment you found a local minima, that local minima will also turn out to be a global minima. So we shall see this and some related results we shall see in today's lecture, and finally, hopefully with time permitting, we shall begin now really to get into control theory, right, because the title of this course is robust control, but up until this point over the last several lectures, it might appear as if we are digressing a bit too much. We are actually indulging ourselves with matrix theory, linear algebra, convex analysis, right, and it might be beginning to appear as though we are digressing quite a bit, but I assure you that all of these tools that we have learnt about and developed will be very handy in subsequent analysis. So hopefully from today's lecture, subject to the availability of time, we shall begin to dive deeper into control theory. Of course, much of it will probably appear revision, like a revision to many of you who have undergone some graduate level courses on controls, and maybe even for those of you who have undergone some undergrad course on control covering modern control theory like state space analysis. Many of these concepts that we will discuss in today's lecture particularly will appear to be familiar. However, we shall try to motivate discussions along certain avenues, and hopefully those will be kind of like a fresh approach to things that you are already aware of, but maybe you haven't thought about in this particular perspective that we are going to present from now on. Okay, enough said. So let's get into this. Let's try to wrap our head around this convexity and wind up with this idea. So, now that we have seen the relation between these hyperplanes and the way in which they help us in separating convex sets that are disjoint, let us take some examples. Okay. Examples of what, you might ask? Well, we will take examples of hyperplanes, right. What sort of hyperplanes are we talking about? So, first of all, we will talk about linear functionals from very specific vector spaces, not just arbitrary vector spaces described by V, but rather in our case the vector spaces will be the n dimensional Euclidean space. So, therefore, our linear functional will be a map from R to the n to R. So, from an n tuple of real numbers to a real number itself, right. So, what is a typical example? Consider that for a given y belonging to Rn, f of x, all right, where of course this x comes from R to the n, can be described as y Hermitian times x, all right. So, this is the way we define the linear functional, all right. Now, you might say, okay, I understand that for a given y which is a constant, this is fixed, because this is after all nothing but, if you think about it for a while, after all what is this y Hermitian? Y Hermitian is the transpose of y, where each entry of y is basically now a conjugate. But now, if you are taking this y to be real, then it really matters not whether you take the conjugate or not, right. So, this is going to lead to y1 x1 plus y2 x2 plus dot 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 till yn xn, where of course x, the n tuple is given by x1 x2 till xn. So, essentially this is an inner product that we have already discussed maybe a few lectures back, right. So, this is a typical linear functional. In order to see that it is a linear functional, all that we need to do is to check that this is indeed linear. So, you just scale up this x by some factor c, which is a real number, and you see that this fx also gets scaled by that same factor c. You take the sum of any two x1 and x2, yeah, and you see that this resultant thing, the resultant real number is also going to be a sum of f of x1 plus f of x2. So, f of x1 plus x2 is going to be f of x1 plus f of x2. All these are straightforward and apparent from the way we define the inner product, right. You understand that these are quite straightforward. Now, the question before us is that, okay, I understand the way we have defined this inner product, this is one way of defining linear functional. Is this the only way of defining linear functional? In other words, if I give you any linear functional on the Euclidean subspace, Euclidean vector space that is, right, is every linear functional tantamount to some such inner product or the other? And the answer is a resounding yes. Okay. So, for that you just take any arbitrary linear functional f, all right, and you want to say define this linear functional, keep its definition abstract, right. But after all, what you are feeding as its argument from its domain, the domain is R to the n, right, and if it has to be linear, then what are the properties it must satisfy? It must satisfy that C1f x1 plus C2f x2 is equal to f of C1 x1 plus C2 x2, all right. So, how do we go about this? So, up until this point we have not really spoken much about the choice of basis, right. So, what do we know about linear maps? We know that if we know what a linear map does to a particular basis set in its domain, then we know what it does to any arbitrary member in its in that particular vector space, right. So, now suppose we have x1 is nothing but summation alpha I vi, where v1 v2 dot 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 till vn is a basis for R to the n, all right. So then we know that f of x1 is going to be nothing but summation, of course we can write I is equal to 1 to n, I is equal to 1 to n, all right. So we can then write this as alpha I f of vi, yeah, that is because of the linearity property that we are now invoking here, yeah, this linearity property we are repeatedly invoking n times, right, yeah, because x1 is after all this. So when you let f act on both of these fellows, x1 on the left and this whole sum on the right, then you can split up the sum in this fashion, all right. Now if I were to write this as I is equal to 1 through n, and remember this is a scalar multiplication, now alpha I is a scalar, f of vi, because when the linear functional acts on a vector it spits out a real number, right. So this f of vi is also a real number. So this is alpha I times, hang on, so this is alpha I times some, let us say fi, where fi is nothing but f of vi, the way I have defined it. But what is this alpha I? Yeah, you see when I take x1 subject to the basis, let us call this, let us give this basis a name, subject to the basis b in terms of the coordinate system b, that is, then this is nothing but alpha 1, alpha 2 dot 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 till alpha n, right. So now can I not write this as, therefore, so this is just for your note, right, note this, that this is ultimately the representation in the coordinate system for x. So now can I not then write this as being the same as equal to, or maybe not, I will not write the summation now, I will just write it in this fashion, f1 f2 dot 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 till fn times alpha 1 alpha 2 dot 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 till alpha n, right. So then what is this f1 f2? Let me call this y star, and this is of course x, or a representation of x subject to some basis, right. So now this is again some y star times x, yeah, which is precisely the form I had given you. So not just the fact that this y star x gives you a linear functional, it turns out that any linear functional, yeah, can be written in this form, all right. So now when we want to define a hyperplane using this linear functional, we also need a real number. So when we equate f of x is equal to c, okay, is it c, maybe I should use a different number, maybe I should use a, yeah, just arbitrary, just my choice of variables, yeah, then this will define a hyperplane, yeah, all the points that satisfy this will be a hyperplane, all right. So then what we have is essentially, if I open this up now, some such inner product you equate to A, and this gives you the equation of the hyperplane. So any hyperplane that you might need to cook up in order to separate convex sets would eventually end up looking like this, right. But of course this y is something that is given, the x is basically the argument that is being fed here to the linear functional, right. Okay. Now let us look at another example. This time we will define a linear functional from the space of n cross n matrices. If you have not already checked, please do check that this is also a vector space. It is basically very straightforward, it is isomorphic, or it has the same structure as n squared tuples, yeah. It is just a different way of writing. You write the n by n matrix, yeah, you write it as an array, like a row and column, n rows n columns. You can also write it up as a stacked vector of size n squared. It is straightforward really, all the properties hold, you can check, subject to the conventional matrix addition and scalar multiplication of matrices, right. Okay. So now let us define it in this fashion, and again we need to now define what our the linear functional of this sort of a fellow would be. So how are we going to define this? Suppose we pick X belonging to R n cross n, all right, and define f of x is equal to the trace of x. Yeah. Is this a linear functional? You can check, of course, in case, just to refresh your memory, what is a trace of a matrix? Trace of a matrix is the sum of its diagonal entries. Yeah, it's the algebraic sum of its diagonal entries. That's what the trace of a matrix is. All right. Now, when we are saying that this is a trace and we are claiming that this is a linear functional, we must be able to prove it. It's pretty straightforward really. You just scale up the whole matrix and of course the diagonal entries also get scaled up by the same factor, and therefore the overall trace, which is nothing but the sum of these diagonal entries, also gets scaled up, right. So, the scalar multiplication property holds, yeah, and then you want to add the trace of two matrices, of course, because entry wise addition occurs in case of matrix addition. Therefore, this trace is clearly a linear functional. But if you want to be more general about this, so this is clearly a, if it is not clear, please try and convince yourself by proving to yourself that this is clearly. So, whenever we say terms like clearly, yeah, you should always be alert, right. Maybe I am trying to gloss over something more complicated, but I assure you here I am not. So, please try that. So, clearly this is a linear functional. But if you want to give it a more general flavor, then we would say that f is such that it is a mapping from R n cross n to R, where it picks some x and maps it to trace of y Hermitian x, where this y is some given matrix, okay, given matrix. So, this is a fixed matrix, just like remember in the inner product case for vectors we had this y, the small y to be given, this little y to be given. Here also this matrix, yeah, of size n cross n is also a given matrix, it is a fixed matrix. The only argument coming in here is this x, yeah, that is the variable, that is the entry that is coming in from the vector space R n cross n, all right. So, what do we need to do now? Again, as before, can we claim, I mean, of course you can check again that this is a linear functional, and in fact if you prove, if you have convinced yourself that this is a linear functional, then the earlier problem reduces to a corollary, because you just substitute y to be the identity matrix and you get the result that of course the trace of a matrix is a linear functional, okay. It's kind of a no-brainer really. But now, just like before, I am going to claim that not only the fact that this is a linear functional, but every linear functional from R n cross n to R is of this form. Again, if you do not trust me, this is going to follow on exactly the same lines, along the same lines as earlier. So, remember for a vector n cross 1 size, yeah, you are living in an n dimensional space, n dimensional Euclidean space. So, you have n bases. Now, when you are talking about an n cross n matrix, yeah, you are living in an n squared dimensional vector space, and therefore you will have n squared members in the basis, all right. So, let now my new basis, again, you know, I have used the same symbol for basis so many times, but I am not going to use a different symbol now. So, do not confuse this with the earlier case, this is a new example. So, I am free to use the same variable again, right, do not hold it against me. So, let us say I call it like E11, E12, likewise till E1n, then E21, E22, till E2n, then I go on like this till I have En1, En2 dot 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 till Enn. So, it is a double indexing I am using. You might say, okay, why didn't you use E1 through En squared? I could have done that. Yeah, but just because a matrix is, after all, entry of a matrix is denoted by a double subscript. So, I have also decided to label the basis with a double subscript, that is all. Yeah, I could have just chosen this to be labeled from 1 through n squared, it would not have mattered at all. Nonetheless, so I have basically n squared members in the basis. So, this be a basis for R n cross n, right. So, now I am then able to write for any x belonging to R n cross n, we have x representable in the form, what symbol should I use? Let me use gamma. Yeah. So, gamma I j E I j summation, double summation. Okay. I mean, I could have written this I j same and written a single summation and just used both the indices. It is just a matter of notation, matter of taste, all right. So, now how many terms will I have? Of course, I will have n squared terms. Yeah. So, for every j I will have n terms. For j is equal to 1, I will have n terms corresponding to the variation of I. For j is equal to 2, I will have another n terms for I. For similarly, for j is equal to n, I will have another n terms for I is equal to 1 to n, right. So, there will be n squared terms where each of these entries in the basis set make an appearance. Again, because this thing, this is a linear functional, I can define this as f of double summation like this, right. And now, if you are not paying close attention, the next thing that I am going to do might confuse you a little, but I am showing you that I am not doing anything crazy here. See, what is this double summation doing after all? It is a compact way of writing a sum of n squared terms, right. Because ultimately, with each of these n squared entries, there is a coefficient associated, which is also indexed by a double index, gamma ij. So, I could have jolly well written this as E1, E2 dot 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 till En squared and written these gammas as gamma 1, gamma 2 dot 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 till gamma n squared. It would not have made any difference whatsoever to my overall analysis. Yeah, this double indexing is something that, if that double indexing is bugging you and you kind of find it difficult to wrap your head around why I am able to write this next step. Yeah. So, the next step is just I pull out both the summations at the same time, and you might think this is a little crazy, but it is not. Yeah, I am not doing anything that is illegitimate. If you want to convince yourself that this is indeed the case, as I said, just relabel those entries in the basis from E1 to En squared, and then you will have exactly the same postulation of this claim as in the earlier case for vectors. Because as I said, an n tuple and an n squared tuple, what difference does it make really? Matrix is nothing but an n squared tuple, an n by n matrix, that is, right. So, now what is this telling me? Yeah, notice that if I now call this, yeah, this if I now call as my Yij, all right, then note that just like in the previous case, I am doing this in a little slow and elaborate fashion because I thought maybe I have not spent enough time, although we have discussed a bit of linear algebra earlier, but I have not spent enough time in focusing on Euclidean spaces in particular, and particularly the space of matrices. So, I just thought maybe I will give you a a direct construction of the matrix in terms of its basis in R n cross n. So, note again as before, x is nothing but this alpha, sorry, what was this? Gamma I have chosen, I am sorry. So, the x is nothing but this gamma ij summation, sorry, not summation, it is a double summation really, Eij, which basically then means that in the compact notation, if I am now writing this in terms of this basis as an n by n matrix, yeah, I would write this as gamma 1 1, gamma 1 2 dot 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 till gamma 1 n, gamma 2 1, gamma 2 2 dot 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 till gamma 2 n dot 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 till gamma n 1, gamma n 2 till gamma n n. Okay. So, this is the matrix representation of x, all right. And what is this Yij now? If I write it in this fashion, yeah, what does this remind you of? What does this remind us of? Yeah. Isn't this reminiscent of the multiplication between two matrices, right? I put it to you that this is after all nothing but same as the multiplication between two matrices, right? But is it just the multiplication? Because now notice that what do I have here? A very special type of multiplication, no? Ultimately, we are not stopping at individual entries only. If you take, so let me write that down here, huh? Let me take two matrices here, both of same size, okay. So, let us say you are first holding this j constant, okay, or rather you can actually flip the order of I and j without any loss as such, right. So, you can actually switch these order of these summation, it will not matter, no, because ultimately both of these are varying in terms of I and j only, right. So, it really does not matter. So, actually what I would call this is, because this is square, yeah, so I would probably call this Yji, yeah, that is what I would call it. Sorry about that, that was a small little, it is just a little bit of a clever trick that I am employing, yeah. Yji is what I would call f of Eij, that is just it, maybe the only trick that you need in this whole problem. And then what does this look like? What is this? If you now focus on this, keeping a fixed j and summing over I, what does this remind you of? This is nothing but if you take Yji times, this is gamma Ij. Gamma Ij is nothing but the ijth entry of the X matrix, right, and you sum over I, right. That means you are taking the jth column, sorry, the jth row of Y here, yeah, and you are taking the jth column. So, this is my Y matrix, this is my X matrix, or rather you can call it Y star, whatever you like, okay. So, you are taking this fellow like this, actually maybe I should call this Yij, right, because then I can just flip it over and I can say this is the jith entry, yeah, sorry about that, again a little bit of confusion. So, this is Yij and then I can write this as Y star or Y transpose, right. So, then what I am doing here is I am just keeping the j fixed and I am multiplying. What will this result in the product? In the product this will result in the jth entry here, yeah. If I take the product here of the jth row with the jth column, jth row of the first matrix with the jth column of the second matrix, I am basically getting jj and I am then summing this over all j. So, basically each individual sum is sitting inside here, this individual sum when I have summed up till here, this is giving me the jth, for a fixed j this is giving the jth diagonal entry of the product, and then when I am summing it over, what I am essentially getting is the trace, because after all I am summing over all the diagonal entries, no. So, this is again, just think about it, this is going to give you nothing but, So, this means that f of x, yeah, is nothing but trace of y conjugate or y transpose Hermitian times x. So, in other words, what we have just established is, if you are dealing with Euclidean spaces, space of n tuple numbers or n cross n array of matrices, and if you want to define linear functionals, yeah, there is only two ways in which you can do that. For the case of n cross 1 vectors, it is the inner product, that is the only kind of linear functional you can define, and for the case of n cross n matrices, it is the trace of y Hermitian times x for some chosen y. So, for a fixed small y, you can define a hyperplane given a particular number, and for a fixed x, for a fixed big Y, you can again define a hyperplane, yeah, corresponding to n cross n matrices, all right. So, this is very interesting, because now we have seen that not only have we seen that these indeed are linear functionals, but that every linear functional must look something like this, okay. So, having seen this and having agreed or convinced ourselves that this is so, now we are going to state the real big result, again in a semi formal manner. So, what is this big result that we were shooting for? So, suppose, so let me just mark this with a hash. So, suppose your vector space is basically a Cartesian product of Hermitian matrices, the space of Hermitian matrices of size n1, space of Hermitian matrices of size n2, likewise. So, remember, the space of matrices, n cross n matrices is a vector space, the space of Hermitian matrices is also a vector space. We have already seen all of that, please convince yourself that this is indeed so. Of course, it is not going to be of the same size, by the way. So, a space of n cross n matrices, arbitrary matrices of size n cross n, has more basis elements, has a greater dimension than the space of n cross n Hermitian matrices. Why so? Because the moment you fix up one entry of the Hermitian matrix, you have already fixed up the entry in the ijth position, you have already fixed up the entry in the jith position as well, right. So, this will be of a lower dimension than the dimension of the corresponding space of matrices of the same size. If you go for a special class of matrices, the Hermitian matrices, that will be a smaller subspace of the overall space of vector space of n cross n matrices, all right. So, let us say we have k such, the Cartesian product of k such space of Hermitian matrices of different sizes being n1, n2, so on till nk cross nk, right, and Cartesian product taken with maybe r to the r, right. So, basically an r tuple. Suppose this is our vector space. So, remember, although this looks like a big vector space because it is obviously blown up, bloated, it is much more bloated than any of these individual vector spaces. Its dimension is actually the sum of the dimensions of the individual vector spaces. Yeah, that is a standard result in linear algebra which we have not proved, but that is true of Cartesian products of finite dimensional vector spaces. Nonetheless, we will not get drawn into that. The point I am trying to make here is that for each of these individual component, or rather each of these individual vector spaces whose Cartesian product goes towards the making of this overall vector space, we know what linear functionals in those smaller vector spaces look like. What I am trying to posit now is that with this knowledge, we can now also provide you with a general structure of a linear functional over a vector space such as this. You might wonder why we are suddenly interested in a vector space that looks so complicated. Again, you have to postpone that and your curiosity to a later lecture, maybe a much later lecture, when we shall actually see that we indeed deal with such vector spaces and we are interested in cooking up linear functionals over such vector spaces that look like this, and thereby even constructing some separating hyperplanes probably. Okay. So, that is our motivation, keep that at the back of your mind, but we will not visit this in quite some time, it will take quite a while Yeah, in a pretty advanced stage of the course we will probably require this. But nonetheless, since we are already discussing this, let us discuss this at one shot so that it gets embedded in our minds. Okay. So, suppose this is our vector space and f from this vector space to the real line is a linear functional. Then this is the same as saying that, so this is an if and only if condition, this is the same as saying that there exist, notice very carefully, there exist y1, y2 dot 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 till yk and yk plus 1, yk plus 2 dot 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 till yk plus r. Yeah, this whole fellow belongs to this vector space. So, any object in this overall vector space, you know, you separate them by commas, that is how you cook up Cartesian products, right. When you have just x cross y, you know, two dimensional x1, x2, we assign the coordinates as x1 comma x2, it is the same notation basically. Yeah. So, you pick, this just means that y1 comes from h n1, y2 comes from h to the n2, yk comes from h to the nk, yeah, and yk plus 1 comes from r, yk plus 2 comes from r, or rather you can also stack them up together and say that yk plus 1 through yk plus r, that comes from r to the r. Okay. Nonetheless, they are just a bunch of r real numbers. Okay. But this overall object, when written in this fashion within this bracket, is a member of this particular vector space. That is how a typical member of the vector space looks like. So, what I am saying is the moment you have defined a linear functional, it means that you definitely have some such constant bunch of k symmetric matrices of size n1 through nk, yeah, square symmetric matrices, and a k tuple and an r tuple of real numbers yk plus 1 through yk plus r, such that for every member of this vector space denoted by this normal v here, yeah, fv, the linear functional is given by fv is equal to summation I is equal to 1 through k trace of yi Hermitian times v I. So, I have not really defined what this v looks like, right. Okay, I will do that later, plus summation I is equal to 1 through, or rather 1 plus k through k plus r yi Hermitian times vi, where again this v is equal to this big V1, V2 dot 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 till Vk comma small v 1 plus k dot 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 till small v k plus r, yeah, and this belongs to the vector space V. So, this is what V looks like, okay. This is what this element V in the vector space V looks like, okay. When you have described this element like this, then it turns out that every single linear functional that you define in this Cartesian product vector space V must look like this for some choice of y1, y2 through till yk, which each of them come from h to the n1, h to the n2 till h to the nk, and yk plus 1, yk plus 2, so on till yk plus r, each of which is a real number. Okay. You might try to flex your muscles here, I mean mathematical muscles here, figuratively speaking, to try and prove this, the proof follows exactly the same line, right. All that you need to do is just to cook up a basis for this Cartesian product of a vector space. So, if you've already guessed what it looks like, then the proof is pretty straightforward. If not, you can also look up some standard textbooks on linear algebra to show that given that you know the basis for two vector spaces, how do you construct a basis, I mean two finite dimensional vector spaces, how do you construct a basis, yeah, for the Cartesian product of those two finite dimensional vector spaces, yeah. And then you will see that it is basically just about writing them, you know, in a nice fashion, right. You put the first element of the basis of the first vector space and put zeros everywhere in the remainder places, right. So, that is how you get all these vector spaces one by one, right. So, you first tabulate. So, essentially what you will be doing is you will be first writing out all the, you will be writing zeros in every other location except for the first location, this first entry here, and this first entry in turn by turn you will be filling out with elements from the basis set for h to the n1. Then you move your attention to the second entry, put the first entry as 0 and the remaining entries from third onwards to 0, and in the second entry you now put all the basis elements one by one. So, you will have n1 entries in the first case, n2 entries for the second case, n3 entries for the third case, and you can keep tabulating and you will find that eventually you will have n1 plus n2 plus n3 dot 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 plus nk plus r, or maybe in this case not nk really, because you know n1 h to the n1 is not really an n1 dimensional vector space, it has a lower dimension. So, maybe the dimension of this one is, say, dimension is equal to d1. So, maybe this dimension is equal to d2. So, you will see the overall dimension is going to be d1 plus d2 plus dot 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 till dk plus r, yeah, that is going to be the overall dimension of V, yeah. So, once you have written the basis in that nice fashion, it is just a manipulation of the proof that we have done earlier, right. You write down the basis for individual vector spaces and you can just push this proof through. So, take that as an exercise. So, proof, I am saying that I have already laid out the pattern for you, but please try this as an exercise, because then you will gain more confidence about your understanding of the subject, okay. So, proof, I am leaving it as an exercise, but go ahead and try to do this yourself, and you should be able to do this by yourself, okay. If not, please revisit the discussions we have had preceding this particular statement or this particular claim, okay. So, that is the one real big result. Before we really wind up on this discussion on convexity, another important object that I feel we should discuss is that which is known as cones. So, we have discussed vector spaces, we have discussed convex hulls, now we discuss what is called cones. So, suppose we have a set Q in a vector space, say V, such that whenever V, any vector V belongs to Q, we also have C times V belonging to Q for all C that is positive, okay. All right. So, then this basically means that you have a particular vector belonging to a set, right. So, every time you have a vector that belongs to a set, all right, you have that, you scale this vector up by any factor and that will also belong to this particular set, yeah. So, it is like, you know, a ray that emanates from one direction and goes along, okay. So, that is what a cone is. So, every time you have one vector, it must be that you scale that vector up in the positive by a positive number and that must also belong to that set. So, such a set is going to be called a cone, but we are not interested in just cones per se, we are also interested in the special kind of cones which we call convex cones. So, what are convex cones? In short, cones that are closed under addition. Yeah. So, what does that mean geometrically? You see, basically again, much as I might not like to draw figures, but here it goes. So, let us say in the 2D or maybe 3D space, whatever. Yeah. Suppose you have this vector belonging to a particular set. Yeah. Then it must be that this entire line in the positive direction must belong to that particular set Q if it is to be a cone. Suppose you have a second vector that also belongs to this set, right, then you must have this line extended indefinitely in the positive direction also belonging to that set if it is to be qualify as a cone. But now if it is also closed under addition, yeah, then you take any scaled version of this, positively scaled version, of course you cannot take it in this direction, so that is not legitimate, yeah, that cannot be done. So you take any positively scaled version of this and any positively scaled version of this, and what do you get? Apply the parallelogram law of vector addition and you will get some vector that belongs within this, yeah, enclosed within this, yeah. So every vector, I leave it to you to check that every vector between these two vectors that I have so specified, yeah, must also belong to that set if it is to be a convex cone, because whenever I pick this from here, I draw a line that is parallel to this and meets this, and I draw a line from here that is parallel to this fellow and meets this, and then I have this particular point or this particular vector represented as some alpha times this vector plus some beta times this vector, right. So every point within those two vectors, so if you have any two vectors, then every vector that is contained within those two must also be part of that set. Therefore, a very quick example of a cone, if I might draw one, is something like this, yeah. So by this I am just indicating that it is broken at that point, but it extends to infinity, it goes all the way to infinity, okay. I have just chosen to take a section of it here to show you that this is a cone. So this may be in 3D, yeah, in the positive octant, okay. However, you can also check that this is a convex cone, while if I were to draw it in this fashion here, so let us say I take, or maybe in 2D itself let me draw it, yeah. So if I take this as my cone as a putative set, okay, the question is this also a convex cone? Yeah, it turns out that this is not a convex cone. Why is this not a convex cone? Yeah, just think about the definition of this convex cone here, right. Apparently if you take two objects from here and you take the linear combination, you would find an object here, and if you take two objects from here and take the linear combination, and you will find another vector here, and this both are part of this, right. So it turns out that all is well, but note, and this is very easy to miss, yeah, note that if you take one object from here and another object from, let us say, here, both of which are part of this set, yeah, and then you take the resultant. Now that resultant is somewhere here, but unfortunately that resultant is something that you have not included as part of your set. So this particular set is not a convex cone, while this particular first example that I have drawn here is a convex cone, okay. So again, much as I might not like to draw these figures here, but I feel that, you know, to illustrate this idea, this figure does a pretty good job, right. So this is an example of something that is a convex cone, and at the same time another example of something, a set that might look uncannily similar, but yet is not really a convex cone, okay. So here I have just taken in 2D, here I have taken x, y and z in 3D, okay. So that is the idea of a convex cone, okay. So a couple of important things, let me go back now to our result on LMIs, okay. And well, I know we have used f to denote linear functional. So, what do I do? Let me use curly f. Okay. So, now it is a reprise. So, this is not related to this discussion, but we will use the property of convexity and convince you. Recall many a lecture back we had discussed, right, that for x belonging to vector space given by this curly x or for x belonging to this vector space we have f such that it is a mapping from this x to the space of Hermitian matrices such that you take this x from this vector space here and it gets mapped to some P matrix, which is basically a Hermitian matrix, right. Okay. And then we saw that LMIs appear in this form, that f of x is less than or equal to some q, where q also belongs to a set of Hermitian matrices. And when we want to read this, we understand this as that this obviously belongs to Hermitian matrices. So, this is basically the difference of two Hermitian matrices. If you bring the q on the other side, this f of x is a Hermitian matrix, q is a Hermitian matrix, and f of x minus q less than or equal to the 0 matrix implies that it is a negative semi-definite matrix. It could have positive, the sign really is not that crucial, right. Anyway, the point being that now consider x1, x2 which satisfy the LMI, let us call this LMI the double star LMI. Okay. So, let us say it satisfies this LMI denoted by double star, alright. Then further let x is equal to mu x1 plus 1 minus mu times x2. Okay. Let us suppose that this is the way we have defined this x. Then what can we say about this? Remember that this f was basically a linear map, right, very important. So, lest we forget, it is after all a linear matrix inequality. So, it is a linear map. So, now f of x is equal to f of mu x1 plus 1 minus mu x2. Of course, here we must define that mu belongs to the interval 0 to 1, the closed interval. Okay. So, mu is a real number between 0 and 1. So, what I am saying is basically, in other words, that this x is a linear combination of x1 and x2, right. Then what can I write this as? This I can further write as mu times f of x1 plus 1 minus mu times f of x2. But recall that this is less than or equal to mu times, if x1 f of x1 is less than q, then this is less than q plus 1 minus mu times, because x2 also satisfies this q, which is nothing but equal to q itself. So, therefore, the set of vectors x belonging to this vector space x which satisfy a particular LMI is a convex set. Okay. Why is this beautiful? The next result that we are going to now present is going to really seal the deal. So essentially then it means that if you are dealing with LMIs, yeah, and you want to minimize, you want to get that particular solution of the LMIs, yeah, then you are basically dealing with a convex optimization problem. You are trying to minimize something over a convex set. You are trying to pick out from amongst all those vectors x which satisfy this LMI, if you want to find out that particular x for which this LMI, yeah, it gives you the minimum, okay, because it is a linear function, right. Then you are basically searching over a convex set, because all those vectors which satisfy this LMI, they form a convex set. That is what we have just proved, right, because if x1 and x2 satisfy the LMI, then a convex combination of x1 and x2 must also satisfy the LMI. Therefore, the solution set, yeah, or maybe the set of, okay, call it a solution set, yeah, solution set means not necessarily the equal to part, but also the ones which satisfy the inequality. So, the set of all possible vectors which satisfy an LMI forms a convex set, and because it forms a convex set, therefore, if we now want to minimize over this set, we will be dealing with a minimization problem, that is a convex optimization problem. And why do we love convex optimization problems? Because the next claim that we are going to make, and we are going to briefly convince you that it is true, right. When searching for an optima, you can replace this with a minima also, right, it really does not matter, over a convex set for a linear objective function, a local minima or maybe optima or minima will also be a global minima or optima. So, in other words, if you manage to find out a local minima, your job is done, and that is why we love convex optimization. So, here is the deal, you are given an LMI, the moment you are given an LMI, you know that if at all there is a non-empty solution set or non-empty set that satisfies, non-empty set of vectors that satisfies that LMI, then such a set must be convex. If that set is convex, then it suffices for me if I want to find out some minimization among that set, okay. If I want to minimize certain objective function, some linear objective function over that set, yeah, then basically I am dealing with a convex optimization problem, and then my problem of finding the global minima reduces to finding just any local minima, because the local minima will in turn be the global minima. Why is this true? Okay. So, again we will do this semi-formally. Let x naught be the minima for Cx, where Cx is basically the cost function or the objective function, and it is a linear cost function, say, for this over a convex set, say Q, okay. Suppose this is the minima, be a local minima, right, because we are trying to see that this local minima will be a global minima. What does this mean in terms of the sophisticated language that we have learned? It just means that if you cook up a neighborhood around x naught, yeah, so if you cook up a neighborhood around x naught, and if you take its intersection with this set Q, yeah, so that means in this particular set x naught is the minima for Cx, yeah, for some choice of neighborhood. So, if it is a local minima, then there does exist a small enough neighborhood, albeit small, but some neighborhood is there which is small, albeit howsoever much small it might be. There does exist some small neighborhood around that point x naught, that vector x naught, such that at least within that small neighborhood and its intersection with the set, the convex set over which you are searching for the minima, at least in that small neighborhood it is the only minima, it is the minimum point for that objective function Cx, yeah. Now, let x1 be another point in Q, right. So, then for mu belonging to 0 comma 1, we have that mu times x1 plus 1 minus mu times x naught belongs to Q, because Q is a convex set. So, x naught and x1 both belong to the convex set Q, therefore, the line joining those 2 points must also belong to the convex set, because Q is convex because of the convexity, right. So, now consider C of mu x1 plus 1 minus mu x naught, okay. So, for small values of mu, say mu belonging to this 0 to some epsilon, some small epsilon, yeah, we know that this C mu, this entry is very close to x naught, right. It is almost 1 minus epsilon x naught, and this x1 has very small weight. So, this is a point very close to x naught. So, then so this we can now also call as a function of mu alone, right, yeah. x1 and x0 are, remember, x1 and x0 are constant points now, okay. x0 is particularly that global local minima point, and x1 is some arbitrary point. So, only mu is varying now. So, this is a function of mu now, yeah. So, for small enough values of mu, we know that f0 is less than or equal to f mu, because it is that local, it is exactly that local property that I am now using. So, if you use small enough mu, it means you are looking at a small neighborhood of this x naught, and therefore, within that small neighborhood at least f x naught is the minima, or rather C x naught is the minima, right. Further, since this is an affine function in mu, yeah, so what can we say about this? Further, notice that f dashed mu is equal to x, if you are differentiating with respect to the scalar, it is just x1 minus x naught, yeah. What should I say? I mean, you just differentiate this, or you just look at, I mean, I should not really technically differentiate it like this, but anyway, you get the point. The point being that if you are differentiating this f as a function of mu only, you get some constant direction, right, you get some constant, alright. So, if you get some constant, yeah, then what can you say about that constant? If in a small neighborhood it is a non-decreasing function, I mean, it is a non-decreasing function, right, because as you venture out from x naught, as you change mu from 0 to some small value, it is non-decreasing. So, that means that constant must be non-negative. So, therefore, for any value of mu that you choose, after all the differentiation is going to be a constant. So, it is going to have the same nature. Notice that this f mu will be globally non-decreasing. Why? Because if it is locally non-decreasing, and because it whatever nature holds locally for this function f, because of the affineness of this function with respect to mu, whatever is the nature of this function in the local domain will be the same nature in the global domain. So, in the local domain I have already proved to you that because it is a local minima, therefore, it is a local minima implying that it is going to be locally non-decreasing, therefore, it must be globally non-decreasing, and if it is globally non-decreasing, this implies that f of 1 is also going to be greater than or equal to f of 0. But what is f of 1? F of 1 is nothing but c of x1 is going to be greater than or equal to c of x0. In other words, what I have just proved to you is the fact that, look, this x1 was arbitrary, x0 was a local minima, but once you found a local minima for a linear cost functional, for a linear cost functional, given that the space over which you are searching is a convex set, set over which you are searching is a convex set, if you encounter a local minima, that local minima suffices as and can be substituted as or thought of as a global minima, and that is why we love LMIs, because in terms of LMIs we have seen that we are always going to be searching over a convex set. Okay. So, with that we will put an end to this discussion on convex sets and their optimization. These will be very handy later on when we get into synthesis and analysis problems pertaining to robust control. Thank you.